So shall I start? Okay. So good morning, everyone. My name is Priya Verma, and I'm a research scholar at IIT Rockford, India, under supervision of Dr. Manoranjan Mishra. So first of all, I would like to thank all the organizer committee to providing me such opportunity to give my work, present my work. So today I want to discuss about this. Okay, so first let me use this pointer. Okay, so today I want to discuss about this viscous fingering instability, which is a non-linear phenomena, and here it is induced by this chemical reaction. So first of all, what is viscous fingering instability? So here it is a hydrodynamic instability which occurs in porous medium at a fluid-fluid interface where, as we can see in this video, when a less viscous fluid displaces a high viscous fluid, the interface get deformed. On the other hand, when a high viscous fluid displaces a less viscous fluid, the interface remains stable. So this is instability has been of special interest for of many decades, as it can be observed in various applications like this CO2 sequestration and this enhanced oil recovery. And also we can see in this laboratory, this chromatography separation techniques due to this presence of this porous medium. And here we are interested to study this reactive viscous fingering. So this is a, 1 second. So this is an experimental evidence for the same. And here they have shown that when the fluids are non-reactive, we get a stable interface in this left column. But when fluids are reactive, we have an unstable interface. And since we are dealing with this radial displacement, where these fluids are displacing each other radially. So this fingering pattern resembles to this diffusion limited aggregation formation or this snowflake formation. And so our contributor will be the numerical to this literature. So now we try to model this flow. So here we consider a second order chemical reaction A plus B goes to C. So here we inject a reactant A, which is displacing the other reactant B, and as they come into contact, they produce C. Okay, under these assumptions, so since we are in this porous medium, so we consider this Darcy's law for the momentum conservation, and for the transport of species, we use this convection diffusion reaction equation. Okay, so this model is already used for this rectilinear displacement for in many literature. Okay, so now I will non-dimensionalize these quantities with this flow with the help of this flow rate Q and this TF final time TF. Okay, so here this is our system of governing equation. Here we have three non-dimensionalized parameters. Here this Peckley, this Temcular, and this RC. These parameters help us to understand this viscous fingering and stability. So here this Peckley shows the relative importance to the convection to diffusion. And so the second parameter is this Temcular number, which shows how fast and slow the chemical reaction rate is. Another parameter, the last parameter is this RC. Here, we have assumed the reactants are of the same viscosity and the product have some viscosity contrast, which induces the instability. And this RC is a kind of measure of that instability, as this RC is a long mobility ratio between the product viscosity and this reactant viscosity. So this is a governing system of equation, which is a non-linear fully coupled partial differential equation. And here, if we consider this RC equals to 0, due to absence of viscosity contrast, we get a stable displacement. And here we can say that reactive forces are not involved yet. But when we consider this RC not equals to 0, so due to the presence of this viscosity contrast, we get an unstable displacement, and here we can say this reactive forces are actively involved. So this is our numerical method which we are using here. So here we have used this pseudo spectral method, which is hybridized by this compact finite difference method. So initially we are provided with this potential flow by the source. So here we encounter our first mathematical challenge in terms of this singularity at origin. To solve the system, we must get rid of this. For that, we introduce a Gaussian source of force sigma. Further, we decompose the velocity into two components, the u potential, which is provided by the source, and this another component is appeared due to this reaction. And we capture that component in terms of this stream function. So we solve this system of equation with this stream function virtuosity formulation. Now we see how this reaction is inducing this instability. So due to product generation, as we have considered this special kind of viscosity profile. So due to product generation, and non-monotonic viscosity profile is generated there with maxima. Okay, when product is high viscous, then this non-monotonic profile is appear with maxima. And here we have two interface. The first interface, which is made by this fluid A and C, and another interface which is made by this fluid B and C. So here at this AC interface, when RC greater than 0, at AC interface we have increasing viscosity profile which induces instability, while this BC interface hinders to grow the instability at this interface. So as a result of this, we have fingering pattern are appearing at the inward interface and they are going towards to the source. On the other hand, when we discuss this RC negative case, the instability are appearing at the outward interface as a result of this minima in the viscosity profile. So further, if we increase this viscosity ratio, so here this fingering pattern get more rigorous. But interestingly, when we consider this displacement for RC2, so even though we have unfavorable viscosity contrast, but still we are able to get this stable displacement. So here we arrive our first consequence of this radial displacement as that reactive forces are not just sufficient to trigger the instability. Okay, so now we try to quantify this deformation at this interface in the in terms of this by the help of this interfacial length, which is the parameter of this product annulus. So here this is the interfacial length curve, and since for the RC equals to 0, we have a stable interface, and for RC2 and -2, this interfacial length is merged with this RC0, and it again shows that this RC2 and -2 is a stable displacement. But if we consider this unstable displacement for RC3 and -3, the interfacial length get deviated. So that time when it's deviated with this stable length, we denote that time as a onset time. And clearly, if we notice that for the RC3 and -3, that means even if we have same viscosity contrast, but still this onset is early for the RC3. So the reason again behind this radial geometry. So if we look again this magnitude of this velocity profile, so it decreases with the radial distance, and here we can say that when the instability appear at the inward interface, it appear with a more convective velocity rather than this outward interface, and these results are completely contradict with the results which are obtained with the rectilinear displacement. So now we see the various type of chemical reaction in terms of this non-dimensionalized parameter dampuller. And here we can see for the fixed viscosity ratio, if we increase the dampuller number due to more product generation, this fingering pattern get more rigorous. Also, if we see this just second column, here we see that there is a transition of the stability of the parameter. Like for the some dampuller value, we have a stable displacement, and for some we have unstable displacement. So if we plot all these value in this dampuller RC phase plane, so we obtain a stable region sandwiched between two unstable regions. And here we can see that this stable region is decreasing with this increasing temporal number. So here one simple question can come our mind, that if we keep on decreasing this temporal number, or if we take a sufficiently large temporal number, whether this stable region will survive or not. To answer that question, we have run some simulations for this temporal infinity case. Temporal tends to infinity. And here clearly we can't apply the same method as we are using for the finite temporal number. So here we have used the same technique used by this group, Nagatsu and David group, Physics of Fluid paper in 2011, where they have solved only one diffusion convection equation, and they are assigning the fluid concentration by utilizing the fact that the reaction is infinitely fast. And here we can see that even though the reaction rate is infinitely fast, even we have this RC not equals to 0, I mean viscosity contrast is present, but still we are able to get this stable displacement. Okay, so this is the so here we can conclude that the reactive forces are not just sufficient to induce the instability. This instability is a result of these three forces: the convection, diffusion, and reaction. The diffusion forces stabilize the flow, the convection forces destabilize the flow. And there is a competition between these two fluids. So here we can conclude our talk, as we have developed a numerical method to understand this radial reactive viscous fingering. Also, we have updated our code for the infinitely fast chemical reaction. We have studied the various type of viscous fingering dynamics for various type of reaction rate, and we have observed that the instability is not induced just by this unfavorable viscosity contrast or this reactive force. It is an it is a result of the interplay between these three forces as convection, reaction, and diffusion. So thank you. Thanks for the ICRB India and UGC India for the financial support. Thank you. And any questions? Welcome for the. Hello.
Hello, so thank you for this nice work. So have you analyzed the effect of the geometry on the yield of the reaction? I mean, have you compared the amount of product that you can generate depending on whether you are radial or rectilinear, or whether it's RC positive or negative? Is there a change in the amount of product you generate?
Yes, ma'am. We have compared that.
So
and there is a change. Yes, ma'am. When we I mean, we can see in the slide. One second, ma'am. Yeah, we can see in this slide we have more deformation for the RC positive gas. That means when the product is high viscous, we have more mixing also, and because of that we have more product generation in the system when we are in radial geometry.
Okay, thank you.